Hello, people joining us. So folks are trickling in and we'll start in just a couple of minutes. Hello, everyone. Welcome.
Hello.
Good morning here in Seattle, and I guess good afternoon over there. And where are you exactly, Gael? What's the name
I'm
of
in
the
the
place?
Alps. I'm in Briançon.
That sounds great.
It is a very nice place.
Yeah.
I'm quite lucky.
Okay, we'll give folks maybe another couple of minutes. I think things have sort of stabilized, and then we'll get in.
So do you have an idea what the attendance is this year?
Yeah, we've had depending on the day and time, we've had between 50 people and 300 people show up. Yeah, but it varies a lot by time of day and
How many
day
people
also.
do you usually have when you're doing it in Seattle?
In Seattle, we usually have 60. This year, we were planning for 70 because we think that would work really well. But as it turned out, that wasn't going to happen. So next year, we're hoping we'll have 70 people in person. Okay, yeah, there's a question already. So let me talk about the hub for a second. There is RAM issues with Binder, and we're running on Jupyter Hub. And the question is, should we select a higher spec machine instance? We have these three different tiers. Which tier did you run on?
I think I took a middle one. How do I know this? I
Take
think
the
I
middle
took
one.
someone. Yeah, I took someone a
I think
middle
the middle
one.
one should work.
Yeah.
And if we get stuck later, we'll do
Right
that.
now it's using 300 megs. I think probably at peak it uses more, but we're looking at we're looking at a few gigs of meg. I already gave a course where some of the students had a Microsoft Surface and ran this on their Microsoft Surface. So
yeah, Binder is a particularly small thing. So maybe I'll actually grab the screen from you just to show.
Sure. Go ahead. Grab it.
I'll grab it just to show how you would update things on the hub. So for folks joining us who want to have this available to them, if you're looking at your hub and it looks roughly like this, you'll hit this new launcher, hit a terminal, and then run git puller. Oh, now I need to remind myself what the git puller command was. Fortunately, we didn't have an embarrassing conversation there in private. There we go. So the command is the following: git puller /nh/curriculum space master space ~curriculum. When you do that, it'll try to fetch it'll fetch the most recent version, so that you have the most recent version on your machine now. And then you should be able to go through and go to the curriculum folder, go to the Thursday machine learning folder, and then Gael will take it from there. Okay, Gael, you can share your screen again.
All right.
So Gael Varoquaux is, your job title is project director, is that correct?
No, research director. Am I sharing my screen?
Research director.
No, okay, I understand what's going on. I need to click on the share screen button. Amazing. Yeah,
research director. Sorry about that. Research director at Inria, and he's been really a core contributor to many projects, both in neuroimaging and in machine learning. So I'll mention scikit-learn and really all through the neuroimaging and Python ecosystem, and I think is an example of someone who takes work that he does within the field of neuroimaging and really pushes it up the stack so that it's broadly very useful in a huge range of domains. I think that's a really good example of doing that. And he'll talk today about using machine learning in fMRI. Take it away, Gael.
Thank you very much. Yeah. So I'd like to talk about using machine learning in fMRI. And so first, I wouldn't like this talk to be a bunch of recipes, or there'll be a notebook. I don't want to execute the notebook just by running Shift Enter. That's not interesting. I'd like to think about why we're doing these things. And so if we're talking about machine learning for fMRI, my talk is mostly going to be about why it's interesting to use machine learning to do fMRI, and I'll give specific examples, of course, and then I'll talk about how we can use Nilearn to implement those IDs, and I'll walk you through a notebook, but I'd rather have a discussion than just walk you through a notebook. Right? So if there are any questions, please do interrupt me. Ariel will be monitoring the Q&A, and please do interrupt me. Discussing machine learning for fMRI, I'll focus on encoding and decoding. There's also a resting state fMRI, but this has been mostly covered by Elizabeth Dupre, I believe yesterday or 2 days ago. fMRI, the line of thoughts that most people sit in, including me often, is that of cognitive neuroscience. And here the agenda is to link psychology, so the science of the mind, and neuroscience, the science of the brain, the organs, and so really we're interested in describing complex behaviors like driving, for instance, which is a combination of understanding the scene and decision making and motor control. So we're interested in explaining this behavior based on their neural implementations. And machine learning, I define machine learning as computational statistics for prediction. Something quite important is that I make no opposition between machine learning and statistics. Machine learning is, a variant of statistics. It's completely fine. It's just focused on out-of-sample properties, and it has a lot of computational aspects to this. What's driving in general in many sciences the use of machine learning is a paradigm shift, because the dimensionality and the complexity of the data is growing, and this enables richer models. And so with those richer models that we will be fitting with machine learning, then we can ask more open-ended questions. And those open-ended questions basically correspond to a larger set of features. But this is shifting the way we work from parameter inference and statistical control on parameters to prediction and statistical control on prediction. And so we need basically to rebuild our methods or scientific methods to use this. And the important thing is that cognitive neuroscience is most often focused on understanding, not predicting. Now, I'm becoming more and more easy with this, because understanding is a very ill-defined word, and quite often understanding just means finding things that we know and basically opening a model and finding things that we know. And these days, I believe that a prediction is a better model selection tool. I'll come back to this. Anyhow, a bit of a gap between just throwing machine learning in something and the goals of science that are to build a narrative that understands things. And so if we look at machine learning and imaging brain activity, we have on the one hand measurements of brain activity, and on the other hand descriptions of behavior and pathology. And our general a goal or general thought is that we're going to be trying to learn associations between the brain and the mind that generalize. And so once we think about generalizing, we think about machine learning. So we're going to be using machine learning for this. And so for instance, if we're given brain images, we can try to predict behavior or pathology. And this can be a diagnosis problem if we're in pathology. But in general, it's really about interpreting these brain images, because most of the time, if you give me a brain image, it's actually quite challenging to interpret. And putting formal interpretation on brain images is basically going to lead us to machine learning-like problems. Now we can go the other way, and we can try to predict brain activity from behavior or pathology. Why is this interesting? Because it will enable us to decompose aspects of behavior that are important for the brain activity. And this is actually a non-trivial task. Behavior is an extremely rich quantity. Well, it's not a quantity, you know, quantifying behavior by itself is a challenge. So if we find quantifications of behavior that predict better brain activity, these are probably better quantifications of behavior. We can also be interested in analyzing brain activity by itself. For instance, when we have resting state. This is potentially useful because then we don't need finely controlled and finely quantified behavior. And finally, we can also be interested in analyzing behavior by itself. And this is quite important because if we need good representations of behavior, we might have more behavior that is available, more recordings of behavior or descriptions of behavior that are available without brain activity. So we can run, you know, massive analysis of this behavior to find structure in it. So these are typically, all these things are problems that I can tackle with machine learning, supervised machine learning for here and here. So when we're predicting brain activity or we're predicting behavior, and unsupervised machine learning or semi-supervised or self-supervised when we're just looking at brain activity or just looking at behavior. So these, I'll be first talking about encoding. So encoding is really, you know, this arrow which goes from behavior to brain activity. And then I'll be talking about decoding, which is the opposite arrow to go from brain activity to behavior. And so let me first start with encoding, so predicting brain responses from stimuli. So the methodology of encoding is that we're building a model of brain responses and we're tuning it on brain activity. And if we're doing this with machine learning, we're going to test this model on left out brain activity. Okay, so we're going to build a model of brain activity given the behavior, and we're going to use, you know, computational modeling, which is basically statistical machine learning, to do this. And then we're going to test whether this model explains well left out brain activity. So if we think about standard analysis, it's actually not that different. So the way standard analysis really works is that we have stimuli, so elementary psychological manipulations. We could have, you know, one stimuli, for instance, a horizontal checkerboard, and another stimuli. And we're going to model the brain response to the stimuli. We're going to you model it using a linear model. That's the standard model. And basically, we're describing the brain activity as a linear function of the conditions. And then what we're going to do is that we're going to basically, you know, contrast those brain maps and conclude things on brain activity. So it's, in a sense, standard analysis is an encoding model. It's just not using machine learning methods. And so standard analysis, and more than standard analysis, a long history of work in neuroscience has come up with models, conceptual models, such as that of the visual system. So the idea being that historically, people have decomposed the stimuli, so the visual stimuli, in elementary aspects of the stimuli and have mapped the response to the stimuli, starting with Hubel and Wiesel, who did experiments by moving a line. So they crafted a specific stimuli and moved the line, and they showed that V1 responds very well to these edges. And so the model of V1 is an edge detector. And so people have, you know, come up with more and more complex stimuli and shown that different regions of the brain responds rather specifically to these more and more complex decompositions of the stimuli. And so we have this idea of a cascade, basically, of regions that are tuned to different aspects of the stimuli, and going from low level to high level, ending up with regions such as the fusiform face area, which is understood as being tuned to faces. And so this whole agenda has worked by crafting features of images and presenting them to individuals, human or non-humans, and testing brain response. And so we can, ask questions such as, is there a face region? We could also, try to contrast foot with face and see if there's a difference between foot and face. We can, ask whether there's a left big toe region. Maybe there's a left big toe neuron in the brain. And so if I want to do this, I'll build an experiment and I will craft stimuli to reveal the left big toe region, and I will acquire lots of data, because I want statistical power, and then I'll do a contrast, I'll oppose this, and most chances is I will find a difference. Why will I find a difference? Because you can never balance everything. And then I'll publish this, and maybe I won't be able to publish this in a good journal because, well, there's no real psychological theory of the left big toe region. But this is showing us the shortcoming of this approach, is that our mapping using the standard analysis, this standard approach, relies on cognitive subtraction. So basically the idea that between my two stimuli or my two conditions, there's an elementary, a meaningful elementary cognitive difference, and a meaningful elementary psychological manipulation. And this by itself is bound to decomposing mental processes. So this by itself is bound to a model of the mental processes that are happening in the conditions. So it only tests a given theory of the mind only inside its paradigm. If I believe in the whole paradigm that encompasses decomposing the stimuli a certain way, then I believe that the mapping that I get is relevant. Now, if I don't believe in the paradigm, then I can challenge the mapping, the left big toe region, because I say, I don't believe in your paradigm, I'm challenging the mapping, the difference that you're getting is not relevant. So in a sense, this approach is basically testing some form of internal consistency and mapping some form of internal consistency. I am not fully satisfied by this. So how do we decompose visual stimuli? And how do we do this in a principled way? Well, if we look at the low-level visual cortex, there's a long-running hypothesis that the reason it is tuned to edges is because it's tuned to the statistics of natural images. These are, there are many ways you can analyze natural images, and when you do this, you find that the fundamental statistics of natural images are basically edges or Gabor filters. And so in a similar way, what drives high-level representations of natural images? And one way of thinking of this problem is to look at our most advanced computational modeling of natural images, and these have been developed in computer vision, and they're basically convolutional neural networks. And what convolutional neural networks do is that they build more and more complex transformations of the inputs. I have an input, and the first layer is basically some form of edge detector Gabor filter. And then on top of this, I'm building a more complex transformation and I'm detecting it. And again, and again, and again. And so what we're seeing here is that convolutional neural networks, which are tools that are really tuned to best solved object recognition problems on natural images, what we see is that they really extract a hierarchy of representations that are more and more complex. And so these representations are driven by the statistics of the natural images and by the task that we're asking, which is visual object recognition. So it makes sense to use these representations to probe the brain, because these are the best representations that we get these days. to solve the problem of natural image, object recognition in natural images. So what we can do then is to use representations of the stimuli that people are looking at to map brain responses. So we're basically going to show images to people, and we're going to feed those images in a convolutional neural net. We're going to obtain transformations of those images, so representations. The lower level ones will be edge detectors, and as we go, we'll have more and more complex representations. And then we can ask, do those representations explain well brain activity? And when we're doing this, we're using an encoding approach. And so if we do this, and when we do this, we are going to have to, so we're going to get very complex representation. You know, if I take a natural image, it has many different edges. So if I describe it in terms of its Gabor filters, I have a very large number of covariates. And to do this, to address this from a statistical standpoint, I will need to use machine learning approaches, and I will need to use things such as out-of-sample prediction to establish the validity of my model, because my model has too many features and is not amenable to standard statistics. So if we do this, and if we look at, you know, which areas of the brain respond best to a model, well, are best described by a model that is built from the low-level features, so Gabor filters, or the mid-level features, or the high-level features. So each time we're looking at which part of the brain responds best, or no, sorry, is best explained by an encoding model. So what we're seeing is that the low-level features are best explained by the primary visual cortex. And as we move up the ladder of the hierarchy, what we're seeing is that higher level descriptions map better higher level regions. So this is an argument to tell us that the representations that the neural network is building are actually good representations of the stimuli to explain the brain responses. So in another way, the brain responses are probably tightly related to those representations. So once we've done this, we can do things such as taking our model. So now we have a model which takes a natural image natural images, transforms them into representations of the input image, and then predicts the brain activity. So we can predict the brain activity given the natural image. So once we have this, then we can start doing things such as probing our model. For instance, doing a standard retinotopy analysis, but on the predicted activity and not on recorded activity. And so if we do this, we find fairly classic retinotopic maps that have been built from our model of the response of the brain to natural images. We can also do standard experiments such as contrasting faces and places. And so based on our model, and if we do this, we find that our model predicts that there is going to be a difference between faces and places in areas such as the FFA and the PPA, so in the corresponding areas of the brain. So why is this interesting? It's interesting because it's giving us a strong generalization because we're going from a paradigm that is built on natural images with results that are related to natural images, and we're showing that they're carrying over to different stimuli with different statistics. So our natural images were in color. The stimuli that we're testing here are black and white. They're framed. They're much more artificial, faces and houses. So what we have here is that we have results that have a wider validity. They go from some some form of ecological validity, which is with natural images, to some form of experimental validity, which is with synthetic images of faces and places. So the reason I'm excited about this is this strong generalization that gives a wider validity to our results. And this generalization is possible only because we're using predictive models, hence machine learning tools. So really the idea here is that when we're using encoding instead of a classic standard analysis, we can have predictive models, we can train them on much richer stimuli, and so we can basically build methods of fMRI that go beyond a handful of contrasts and that test cognitive models beyond simple dissociations such as opposing faces and places. Because once again, those simple dissociations are only interpretable inside the cognitive theory that underlies the event. Whereas a predictive model can make predictions that go beyond this and be tested beyond a set of stimuli. Now, are there any questions on this, by the way? I realize this is quite, no questions so far. Well, please do not
there haven't been any questions so far, but this is a good point to ask questions.
And if you have any questions, just ask him and Ariel will interrupt me. So, I've shown how encoding can be used to develop richer models of the behavior. Now I'd like to talk a bit about decoding. And first, I'd like to stress the reverse inference fallacy, which can be very easily summarized by the following example. All dogs eat meat. I eat meat, therefore I'm a dog. There's a clear fallacy here, and it's a clear logical fallacy. It's also known as the fallacy of the converse. The reverse implication is not true. The two premises do not imply that I am a dog. Why is this relevant to the brain? It's relevant because we have so far studied the implication going from behavior to brain activity, but often we would like to conclude on brain activity given behavior.
Gael, just to jump in, there are a couple of questions, so I'm going to interrupt you and then you can come back to this. So the first one is, what is meant by an edge?
So what is meant by an edge? Well, that's actually a very good question. There are many different ways of defining an edge. You can take the conceptual notion of edge. And if you take the conceptual notion of edge, how do you instantiate it? And then there are different ways of instantiating it. And that's basically the state of vision science until I said the mid-90s. It's not clear that the exact definition of an edge matters. There are different ways of defining an edge that will work well to explain brain activity. The definition that I am taking is a Gabor filter, which is almost the same thing as a wavelength. Mm-hmm. So it's an edge detector.
The second question here is, how can encoding be applied in the context of the clinic as opposed to neuroscience? I think here it's like as opposed to sort of basic research.
Yeah, as opposed to cognitive neuroscience. Well, take disorders or pathologies. They're usually studied in isolation. I will look at autism and attention deficit separately. Or I will look at schizophrenia and attention deficit separately. And so, if I do this, I'm going to, and the classical way of doing it is to say, well, I'm going to look at, I'm going to contrast people with autism. And, for instance, I can contrast volumetric brain mapping of people with autism with people with attentional deficit. Or I can contrast people with schizophrenia and people with attentional deficit. If I do this, I'm basically using standard analysis. Now, one way of doing things would be to say, no, I'm going to give a much richer descriptions of my subject. I'm going to describe my subject with many, many, many traits. If I describe my subjects with many traits, then I start having a high-dimensional description of subjects, and then I will need to start using machine learning to basically predict what the gray matter density, for instance, of a subject is, given that rich description of his behavior, normal and pathological. So this would be one way of doing things in the clinic. I don't know if it's been done. I think it would be interesting to do it. The challenge, of course, is going to have rich enough data. What do I mean by out of sample prediction? Well, most statistics tells you something about the data you have. And I'm given data, and given that data, what can I tell on the parameters of my model? That's the classic question that statistics answers. Whether I'm going to be looking at a posterior of those parameters, or whether I'm going to try to see whether they can be explained under a null model. What I mean by out of sample prediction is, if you were to give me new data that is drawn from the same distribution of the data that I have already seen, how would my model perform? So if I have a classification model, my model is going to separate autism from control. My question is not, given this batch of images, how does my model perform? That is not an interesting question. My question is, if you were to give me new images, what is my expected error rate? What is my expected risk? This is also what we call generalization. Did I answer all the questions?
I believe so for now, yes. So.
All right, well, do not hesitate to ask more. So, going back to my reverse inference problem, if we take a step back and we look at how cognitive neuroimaging works, it's also partly true for clinical neuroimaging. The questions we ask are, what is the neural support of a given function? But a question that we would like to ask often, and that is often discussed in the discussions of papers, is, what is the function of a given brain module? Now, the problem is that brain mapping is using task-evoked activity. So basically, brain mapping, the activity that we're observing in brain mapping is conditional on a given task. And on top of this, we cast contrast to isolate effects. But when we've seen this, we've seen only a handful of tasks. So we can, if our task decomposition is right, we can maybe answer what the neural support of a given function is, but we cannot answer what the function of a given module is, because we need to reverse the implication. If I've seen that a brain area lights up is activated with faces and not places, I cannot claim that this brain area is specific to faces. I want to claim that this brain area is specific to faces. I need to probe all the possible tasks and behavior on Earth and show that this brain area is activated only when there's a face, in which case I can claim specificity. So the answer to my second question is a reverse inference. It is an implication that is not naturally supported by a given brain, by a given task fMRI experiment. Now, this is a well-known fallacy that has been very well explained by Russ Poldrack in the 2006 paper. So, is there a face area? It might seem consensual because prominent people have advocated for this, but not everybody believes there is such a simple story that there is an area that is absolutely specific to faces. And it's actually very difficult to establish. So one agenda to answer this question is to use decoding. So basically to predict the behavior given the brain. And the agenda is to then use decoding to find regions that predict a specific aspect of observed cognition. To do this, we will need a large cognitive coverage. We will need to show that activity in these regions enables to discriminate behavior, to predict a specific aspect of behavior across a wide variety of tasks. And so the idea being that to use decoding to support reverse inference, you're going to try to show that some brain regions specifically predict some aspect of the behavior across many different tasks. And then the challenge is that to get such a very wide variety of tasks, you're in a pragmatic way. The best way to do this these days is to aggregate many paradigms and possibly many different studies. And then the challenge is that it's difficult to assign specific description of behavior across those different paradigms because those different paradigms are formulated in a different way. So the basic tool that is used is linear models, and the reason linear models are interesting for decoding is that their coefficients are brain maps. A linear model in decoding has a design matrix that is made by the observed brain activity and is trying to estimate coefficients, so brain map, that are such that the product of the design matrix with the coefficients will predict the target. And so, what people do is that they run decoding using linear models. And so there's a wide variety of different linear models, for instance, linear SVMs, and they look at the coefficients of the linear SVM, and they conclude that where the coefficients are high, the region must be related to the specific discrimination that we're interested in. So, for instance, to look at a historical problem, we're looking at faces versus houses, and we're looking at the brain map of a support vector machine, and we're finding that well, there's loading in this region, so this region must be related to face versus house discrimination. Now I get a different model. There's a wide variety of different linear models, and you can use, for instance, a sparse model. If I use a sparse model, I get only a handful of voxels that discriminates, but my error rate is lower. So I should probably conclude that this is a more relevant brain map. And I can use a ridge. Ridge is another form of linear model. And if I do this, I get an even lower error rate. So that's probably a better model. However, the brain map doesn't look like my prior assumptions. And specifically, it doesn't really outline the FFA or the PPA. So the challenge being here that when we're using decoders and concluding on the brain maps, it's hard to have statistical guarantee on those brain maps because the decoder by itself only controls the error rate. And if we want to put a tiny amount of math on this, the problem we have is that we have an inverse problem where we're minimizing an error rate. So minimizing how many times we get it wrong in our decoding problem, but we have a small number of observations and a very large number of features. So this inverse problem is ill-posed in the sense that many different brain maps are going to give the same prediction error. I can change my brain map, and on the data that I've seen, I'll have the same prediction error. And so the choice of the brain maps is driven by the implicit behavior, the implicit prior of the decoder that I'm using. And the decoders, such as SVM, do not have priors that are tuned in any way that are built in any way to reflect something about the brain. And so one example is the sparse estimator, where the prior, I'm not going to go into math, but the prior is basically tells me, try to choose as little voxels as possible that predict well the behavior. And if I do this by construction, I will have a map that is very sparse because it's the prior of the decoder. So a better prior is to use sparsity on the gradients of the image. The reason I say it's a better prior is that a sparse decoder will tend to segment, to select a very small number of voxels. And if you have two redundant voxels, it will select only one of the two, right? I have two voxels, those two voxels are responding in the same way. And the sparse models will detect that they're responding in the same way and will select only one of the two. So if I do this, I'm going to select a subset of the region that I'm interested in. So one way to go around this is to use total variation penalty, which is to say, basically, I'm going to try to select regions on which the spatial gradient is sparse. So basically, I'm going to start to select regions that are locally structured. And this is what we do here. And what you can see is that this segments really well the FFA and the PPA. And so why does this work is because the prior of selecting regions, actually, so what we do here in what we call TVL1 is that we combine this prior of region and this prior sparsity. And the resulting prior is basically, can basically be summarized as, please select a small number of voxels that are grouped together that predict well the behavior. And this is well adapted to the intuition of functional units of the brain, which are made of locally connected set of voxels. So if there's one take-home message that you can take from this slide is that different decoders will give different regions. And ideally, I would push you to use a decoder that has a prior that is consistent with our picture of the brain. And the TVL1 decoder is one of these. Now, we have a more recent work. So the TVL1 decoder is implemented in Nilearn under the SpaceNet module. And we have, so the drawback of the TVL1 decoder is it's slow. And in Nilearn, we hear about fast models because then they can be used on commodity hardware. And more recently, in the last few years, we came up with different strategies that have a similar behavior, but are much faster. And just to give a quick idea of how they work, and the most recent version is called FREM, for fast, regularized, and sample of models. And the idea is that we're going to use very fast models that are suboptimal, and we're going to average many of them. And the benefit of averaging many of them is it gives you very stable maps. And to capture this idea of functional units, what we're going to do is that we're going to learn parcellations of the brain by some fast clustering. And we're going to estimate linear models on those parcellations, and we're going to average the result. And we can do this many times, and each time we're going to perturb a bit the data. And so each time we're going to get slightly different parcellations, and so slightly different sparse linear models, and the result is basically a combination of all this. So if we do this, we get a prediction score that is the best performer compared to, so these are empirical results that have been done across many different decoding tasks. So we get a good prediction score, but unlike L1 models, we get much more stable brain maps. And the reason is that L1 models predict well, but they tend to select a subset of the voxels. And see, this subset is very, very unstable. I might select this voxel or this voxel, voxel. So randoming this one or this, it gives me a very unstable model. The friend will group these together and enhance it. So I get much better stability than the other approaches. And I get a computational speed that is quite comfortable, so slower than SVMs, but significantly faster than the other spatial models. So
yeah, can I stop you here, because there are a few questions that have come up, and
sure.
I'd like to sort of try to address those. So I'll start maybe with Ben asking. Maybe I'll start with the more specific, and then I'll go to this general question. So Ben asks, if you run several decoder strategies of the same data to see which one fits best, do you need to correct for multiple comparisons?
That's a very good question. That's actually, you should. You really should. However, so the way, I haven't gone into the methodology of machine learning, the way this should be done according to machine learning principles is that you should separate your data and you should hold out data. So leave data untouched. You should run your analysis, including cross-validation, and select your best model, and then test this best model on the left-out data. Multiple comparison works for p-values. So you might, conclude that, oh, out of these 3 models, there's no significant difference, which would be a very good conclusion. And then the question is, how do I now know what is my actual prediction performance taking the best model? Oop, I take out my left out data, my held out data, and I take my best model and I apply it to this held out data. This is how you should do it. It's the same problem as multiple comparison.
Another question here is, when using the TV decoder, are the features flattened like in L1 and L2 models? If they are, then how do you compensate for loss of spatial and
Okay,
not entirely, some kind of spatial information here?
Well, they're smooth. They're not flattened. They're smooth in a way. It's the intuition of sparsity in the gradient is actually slightly incorrect. I don't want to go into details, but it's more of a smoothing on the gradient of the image. And I claim you don't lose spatial resolution because I claim you don't have this spatial resolution. This is controversial and MR physicists get annoyed. But if I've seen the response to a brain image, to a given task, only 100 times, my limit to my resolution is not how many voxels I have in my image, how many times I do a task. And now, if you make the hypothesis that those voxels are all independent, then you can use mass univariate analysis and you can do the analysis on each voxel. And then, sure, you're not too limited by your number of stimuli presentations. But if you make a multivariate analysis, then you're most often limited by your number of stimuli presentation. So you don't have that set solution.
Okay, Ben asks also, when one does decoding, can you decode performance on behavior A while controlling for performance on behaviors B and C?
Oh, that's an interesting question. We would get in a very long discussion there.
So maybe, you know what, let's maybe not. Let's punt this one and say, let's ask this one on Slack also, and then move on with your lecture. There is one more question. So Ben, I'm sorry, but let's take this one on Slack. Or Neurostars, if you're watching this later on, we can also ask this on Neurostars. The question is, could you give a brief explanation of the different machine learning models and in which scenarios it is best to choose each one of them?
So, well, machine learning models, there is a gazillion.
But maybe of the ones that you're showing here, like SVM versus GraphNet.
So if you're getting brain images, if you have inputs that are brain images, most likely you want to use linear models. First thing, because you have way too many features compared to the number of samples, and you want to stay in your model. These are what are going to predict most, unless you're in very uncommon situations with extremely large cohorts. By extremely large, I mean, you know, dozens of thousands of individuals. Now, which one should you use? My bias is you should use TVL1 or FREM. And I think gives a very good benchmark, but, you know, never trust a scientist on his own results. Always check them. Now, it's a bit of a problem because the more models you're gonna try, the more you risk to overfit. So ideally, I think what we should have is an independent paper validating our biases and showing that these are good models. But what we found is that FREM and are the best models.
Cool. Oh, and then one more question. What are essential differences in machine learning processing EEG data compared to voxels? Maybe let's take that one as a discussion question later on. So Alex, sorry, but I'll punt that one to later and come back and ask that one again later on, or I'll leave it open for now.
I don't know if we have a half hour after my course, but I'll be staying online if people want to discuss things.
Yeah, we can, after we log off, you can stay on Slack and answer more questions about these things. Okay, so you can go ahead and continue.
Okay. So, but which model should you use? The answer is on the slide, and in the paper, on the FREM paper, you should use the FREM model. I'm biased, but please confirm my biases. Okay. So if we have time, we'll play with these things on the notebook. We'll compare those models on the notebook once I'm done with those slides, which also tells me I need to move faster, but I'm getting to the end of my lecture. So, you know, all the questions on the validity of machine learning, whether they're on which model we should use, which parameter we should set, or do my results generalize, all these are done, or well, answered using machine learning methodology, which is basically cross-validation, and the idea being that you're going to test a given model on the same data. The whole validity of machine learning is based on this. And yes, sometimes there are theoretical arguments that allow you to say certain things, but honestly, in my opinion, they're brittle. They don't apply robustly to neuroimaging data, and the validity of machine learning is based on cross-validation. Now, there's one caveat, is that if I don't have enough data, cross-validation becomes brittle also. And to give you one example, there was a Gael competition that was run a few years ago to predict schizophrenia based on fMRI. And this Gael competition had two left out data set, as often with Gael competitions, a private data set that is never shown to the competitors, and a public leaderboard where the results of testing the model are shown. And what I'm showing you here is the distribution between the observed error on the public and the private leaderboard. And so, you know, this distribution basically ranges from, well, has significant mass from -15% to +14%. When you think of it, that's pretty huge, because that's a 30% difference between, well, the 95% confidence interval are plus and minus 30%. So plus and minus 30%, it tells you on the same data, I could have 50% chance of prediction, or 70. I could be reporting this. Why is this? Quite simple. The size of the test set were 30 and 25. So they were tiny test sets. Tiny by the standards of machine learning, not tiny by the standards of brain imaging. And by the way, in this competition, the person who won the competition was the first submission ever written. So first person writes something, sends the code, wins the competition. So all this is well explained if we think about the sampling noise on the test set. And this can very easily be modeled by binomial law. The idea being my classifier can be modeled as a coin flip, but ideally a biased coin flip, because if it's not biased, it's choosing at random both options. So my classifier error can be modeled by a coin flip. And so if I have only 30 subjects in my test set, I'm flipping the coin 30 times. And flipping the coin 30 times does not give me a very good estimate of whether the coin is biased or not. And so these are empirical distribution of the error for 30 subjects, 100, 200, 300, 1,000. And I'd just like to stress that the confidence intervals are bloody large. And even with 1,000 subjects, the confidence intervals are plus and minus 3%. And most papers that I see that claim that they have designed a new method that improves machine learning, including mine, by the way, that improves machine learning on brain images, do not have an improvement that is greater than 6%. That's a pretty huge improvement. So most of these improvements are adequately explained by chance. So that's quite a disastrous a consequence on the field, because it means that methods researchers like me are very likely to report models that look good, but are simply, this seemingly good performance is simply explained by chance. And so the way, by the way, we've gone around this is to do benchmarks across many different experiments, which increases the sample size. So that's for methods results. And for application results, there's a very big danger is to test a bunch of different approaches. For instance, all the decoders that I've mentioned before, and pick the best one, in which case the problem is that you're mining the tail of this distribution, and in which case you can't trust your results anymore. So there are two ways out of this. One is to stick to standard models and really only use these. The other one is to have larger data sets. Ideally, we should do both. And those standard models should be established by thorough benchmarks across many different data sets. So one last thing, I'm done, but I'd like to talk a bit about Nilearn. You've already had an introduction about Nilearn. The goal of Nilearn is to provide the tools that I've discussed to users, is to enable users to do science with machine learning and do neuroimaging with machine learning. Something that we've recently added to Nilearn is that we've recently added standard analysis to Nilearn, just to ease the whole line. And so Nilearn is these days providing a full pipeline that goes from data extraction, not pre-processing. So no realignment, no motion correction and these things. So we take pre-processed data. For instance, you can pre-process your data using fMRI prep. And from this, provide the whole pipeline that goes from data extraction, analysis, and visualization. Our goals are to be easy to use and low resources to enable people do their analysis on commodity hardware. And that we're an open community. We have more and more contributors that are not historically linked to the original contributors of the package. We think it's very important to have a more vibrant community and also to have a better package in the long run. Okay, so I'm going to wrap up on this part to take a step back. I've talked about decoding, going from measurements of brain activity or brain images to descriptions of behavior and pathology. I've talked about the tools that we can use to do this and why it's relevant, and why it's relevant in cognitive neuroimaging can be to identify regions that are specific to a given aspect of cognition. I've talked about encoding, so predicting brain activity given description of tasks and pathology. Why is this relevant? Why is this interesting? Because you can give richer descriptions of behavior, and so you no longer need to isolate oppositions in your behavior, and hence you can have wider, broader models of cognition. And I haven't talked about resting states. I know Elizabeth Dupré covered this in her talk a couple days ago. The reason resting state is quite important is because data without labels, so without controlled behavior, is cheaper to acquire and is more universal. Thank you. Are there any questions on this part?
Yeah, so there are a couple of questions in the Q&A that I'll mention. So Keith asked, and both of these I think are about the cross-validation failure part. Are the performance metrics similar for using moving searchlights rather than whole brain data for this cross-validation failure issue?
I'd say it's worse for searchlight. I don't do searchlight, partly because I do not like it from a theoretical perspective, but you know, you need to add to searchlight correction for multiple comparisons. So on top of this, if you're going to do searchlight with, I don't know, 10,000 searchlight spheres, you need to correct for multiple comparisons on those 10,000 searchlight spheres. So you know, it doesn't look like there's a good statistical power there.
Yeah. And then Isabel asked, what would be the ultimate sample size minimum that could be used when performing machine learning analyses on fMRI data? Is there a rule of thumb? Do you have some rule of thumb for when it's too little?
There's no good rule of thumb because the higher the effect size, the less sample you have. However, for
I mean, you had these error bars that were like 20% error at the top. So if you have a 20% effect, then that might be fine, right?
Well, if you have a 20% effect and you don't try out different models, because if you try out different models, you start minding those tails. A bunch of different papers, including ours with Respoltrak, this one with Respoltrak, but others, for clinical applications of neuroimaging, give the guideline that you shouldn't really do a study without 300 subjects. There's been a bunch of rather independent papers that come up with this number. Honestly, this number is a compromise. You know, it's clearly bigger is better, but I will start, you know, trusting results when you have 300 subjects. For fMRI, it's slightly different. So for task-based fMRI, it's slightly different because you don't always have independence across your trials. So it depends somewhat on the independent structure of the trial.
And then Hina asked sort of a follow-up that relates to this. How was this differ between healthy and clinical populations? And I think just to paraphrase on that question, if your subjects are if your subject population is very heterogeneous, this will be worse, right?
I'm not sure. I think heterogeneity is a huge straw man. It's something people have been worried about since, you know, ever in psychiatry. And I don't think heterogeneity makes the approach invalid in any way. It may break your prediction. So if you have heterogeneous subjects, it will break your prediction. Fine, you should see this. And by the way, if you pile up more subjects, so the idea of heterogeneity, for instance, if I have controls, autism A and autism B, right? I have controls, autism A, autism B. Autism A and autism differ. Now, if I have plenty of data and I created autism A from autism B, I can nonlinear model that can separate those two populations, or even the continuity that's in between the two, from control. So, you know,
Gael, sorry, you cut out a little bit on the audio. Could you just repeat that? You have the two groups of the patients of autism A and autism B and the controls. Could you repeat from there?
I have autism A, autism B. So autism B is here, autism A is here. And clearly, if I use a linear model to separate autism A from control, it won't work for autism B. If I use another linear model, it won't work. But if I have enough data, so I don't know, 10,000, to learn a non-linear model, then the heterogeneity of the population is no problem. So
it's a bit about, if you have more data, you can fit more complex models, you can incorporate heterogeneity of the patient population into your model and solve that problem.
Yeah.
Great.
And if I don't have enough data, I should see this in the performance of the model.
Somebody asks, rather than increasing sample size, what about increasing the number of trials? Would this help at all?
Yeah. Well, I call trial samples, by the way. If I'm doing cognitive neuroimaging, then trials are samples. They're not fully independent, so I need to worry a bit about this. But
it depends on the sort of the effective degrees of freedom that you have.
Yeah.
Or end up being important. Okay, another question. Daniel asks, it looks like train test splits are somewhat better than leave one out for confidence intervals. Would increasing the number of splits or changing the percent in the test set improve the confidence interval?
That's a really good question. I have a paper a while ago that looks at this and basically finds things that are well known in machine learning is that leave one out is not a good option. You should avoid it. And the option is to take 20% splits and 20% in a test set and do many random splits and many as much as you can afford. There's of course a diminishing returns, right? So typically 50 split is enough. One caveat here is that you want your test set to be independent from your train set. So if you have trials that are successive, you shouldn't randomly subsample them because it's going to be, I'm going to be able to predict something about a trial by simply noticing that the brain activity is similar to the trial before and the trial after. And that's just due to the autocorrelation of the signal and absolutely not due to a specific aspect of brain activity.
Okay, there's a couple more questions here. What do you think about non-parametric tests to probe the significance, like bootstrapping, permutation tests, and so on, rather than relying on the p-values of parametric tests?
No, that's fine. I always prefer non-parametric tests, and permutation tests are great. They won't solve the statistical power issue, right? They might reveal it, which is really good, but they won't solve it. What I worry most in this statistical power issue, by the way, is the unreported degree of freedom where people have tried many things and have basically mined this tail and are reporting only this. This is what I worry about. This is something that as a reviewer, I cannot see. This is something as a PI I cannot see. This is something that risks undermining our field. Okay. Aggregating across data sets. I think this is a very promising agenda. We've done a bit of work on this. It becomes quite challenging because the labels are often inconsistent across data sets. But if you're a methods developer, I think this is the most promising thing to be looking at. I think it's promising because it increases sample sizes, but also it's promising because it gives more external validity. If I have a biomarker of autism, ideally I would like it to work on the New York population and the Boston population, also maybe on the Paris population. In-sample model fits fails, but external validation to completely independent sample is successful. Could this model be considered as, what do you mean by in-sample model fits? You're going to be using a given measure of model fit. And if you're using the same measure of model fit as the external validation, I don't really see how it could fail.
In a sense, that's what regularization does, right? It makes the model fail on the in-sample model just a little bit so that you can do better in generalization.
Right, but if you're getting lower accuracy in sample than out of sample, you're probably underfitting and putting too much regularization. No, the thing is, the thing is that the statistical tools used for in-sample fit are often different than the statistical tool used by machine learning. So people might be looking at some p-value or something like this, which may fail simply for multiple comparisons, but the model may predict. Does that make sense?
Yeah. Okay, Rogers corrects the record for the 2014 Kaggle competition. Although the winning team was called Solution Draft, I don't think that this was the that this was the very first submission during the event.
That might be correct. Yeah. Sorry.
You mentioned leave one out is worse. Let's take this one as the last question and then we can move on. You mentioned that leave one out is worse than train test. Could you elaborate more on why this might be?
Yeah. So why should you avoid leave one out? Well, when you're doing cross-validation, you're doing a trade-off between how much data do you give to your model to fit and how much data do you give to assess the quality of the model. And when you leave one out, you're doing a single data point to assess the quality of a given model. So you do many of those multiple models, but they only have a single data point. So each time you have a horrendous assessment of their quality. And to give you an extreme case, and somewhat of a fun case, I have a perfectly balanced data set. I have 50 subject A, 50 subject B. I do leave one out. My train set has an imbalanced data set. And if my learner is stupid, it can learn to predict only the majority class. I have 50 and 49. And my test set is now inversely imbalanced. I can't really get a good assessment of what's going on. That's a historical example, by the way. But the point being that if we leave one out, you just don't have enough data in your test set to probe correctly a given model.
Okay, cool. Okay, and I'll let you move on now.
Yeah, let's move on to the notebook. I might not have time to cover it, but that's good because I don't really like to cover it fully because I don't really like just shift entering through a notebook. So if you go to the hub and you go to curriculum and to Thursday machine learning Varoquaux, how do you find that?
It's on. You have to click on the folder icon on the left because you closed off the folder.
I closed the folder icon. Yeah. Okay, there you go. And then you see the notebook, and then you can open it. Okay. So then you get to this notebook. So what this notebook is, it's an introduction to decoding using Nilearn. And this disclaimer, it gets more full, more fun, and prettier when we release the new version of Nilearn, which should happen anytime soon. But I would rather do this with the current version of Nilearn. So we can just quote unquote shift enter through this notebook. So basically run things. So you can also just click and run all. Anyhow, the point being, I can walk you through a bit what's happening in there. First, we're downloading some example data. This is example data. It's there for didactic reasons. It's not there for research reason. It's awesome data. Thank you, Jim XP, for sharing it. But it's old data. We should be using probably more recent data. So the data, and then here we retrieve the file name. And so this is just a file name. It's a string with a file name. And then we can look at it. So it's fMRI data. So it's a 4D image. And the tools in Nilearn to look at brain images, look at 3D images. So the first thing we can do is that we can compute the mean image. So for this, we use Nilearn.image.mean image. And then we can use the view image function. And we're telling it not to threshold anything. So view image works in the notebook and gives us interactive visualization. So this is our data. This is our average fMRI data, as you can see. Okay. So that's useful just to check that it's not obviously wrong or crop or not what I think I have. So with this data also comes a mask of the ventral temporal cortex. So it's downloaded with the rest of the data, and I can retrieve it here. The square bracket 0 is because I might be downloading multiple subjects, and I might want the mask only of the first subject, of the second subject, etc. So here I'm plotting this mask on the anatomy of the first subject using fMRI. And you can't see anything because the contrast is too poor, so I can inverse dim, which is decrease the contrast. So dim equals -1 will inverse dim. Ooh, now I can see things better. And so what you can see is that this mask is a mask that was established by the original authors to look at, to select voxels in the ventral temporal stream. And so now what we're going to do is that we're going to extract the data from this image, but this image is a 4D image, is a time series, instead of time series. We're going to extract the data on per mask. Okay, so we're going to go from a 4D image to a set of time series on this mask. And to do this, we're going to use what we call the nifty masker. So the nifty masker is a fairly central part of Nilearn, which will apply a mask to an image to extract the time series. So, and there's a bunch of other maskers, and they all live in what we call input data. And so we import it, we create an object that's called masker, and we tell it that we want to extract on the mask image that we have, so it's the ventral temporal mask, and we tell it that we also want, during the extraction, we want it to standardize the time series. And so then we call fit transform. So fit transform will transform the image into time series. It will basically do the extraction. Once we've called fit transform, or just fit, we can generate a report from the masker. And so if we do generate report, we get a useful summary of what's being done. So it's supposed to show the input nifty image overlaid on the contour of the mask. Honestly, between us, I don't see the input nifty image. I don't know what went wrong here. It's interesting. If people want to investigate this and fix this in Nilearn, send the pull request to fix this in Nilearn, that would be really interesting. And so we also get the parameters, including a bunch of default parameters. So we can see that there was no smoothing, there was standardization, there was no low pass filtering, no high pass filtering, no detrending, okay? And this can be useful to share across coworkers to be able to inspect the pipeline and see what has happened. So, fit transform has returned an object, fMRI mask. What is it? I can print it, and if I print it, I see that it's, I can also display it without printing. I see that it's an array of numbers, okay? We can look at the shape. The shape is, oh, I know what happened. I need to re-extract. We can look at the shape. Okay, so now this needs to, okay, so the shape was a 2D number. Sorry, it was 2 numbers, yeah. So 2 numbers, we have 1452 times 464. So, do you want to take a guess in your head? Or Ariel, do you want to tell me what those 2 numbers are?
No, I'm not sure. Sorry.
Okay. The first number is the number of time points. And the second number is the number of voxels in the mask. Okay. So I have 1400 time points and 400 and something voxels in the mask. Okay. So this is, so we don't have the figure here. If you look at the documentation, you'll have the figure. We don't have. So what happens is they're taking a 4D image that is made of 1400 3D images, and we're converting it into a 2D array that is made of 1400, well, of 1400 vectors of dimension and number of voxels in the mask, okay? And now what we can do is that we can plot these time series. And so here we're plotting the 3 first ones, and we're removing the first 5 voxels and the last. And we could also plot them completely. So here we're plotting the three first ones. Oh no, we were not removing, we're just limiting because it was too long. Okay. So the 3 voxels, this is the time series of the 3 voxels. Now, if we want to do decoding, so now we're happy we've extracted time series from the fMRI data, and we have a matrix that is a matrix of time series. And this matrix of time series, it's a 2D matrix, and this is what machine learning takes. This is what a scikit-learn will take. We can just give this 2D matrix to scikit-learn, but we also need to know what behavior we want to predict. And so here we have the behavior that is given to us in a CSV file that we can run with, that we can load with pandas. And if we load it with pandas, whoops. If we load it with pandas, we get a panda data frame that has 2 columns. One that is called label, and it's the label of the behavior that's made. So you can see here that during the first 5 TRs, the behavior was rest. And we have chunks. Chunks is the session ID because this experiment was run doing multiple sessions, actually 12. And so this number gives the session ID. And so we can retrieve the labels, and we'll call this condition. So we're retrieving the labels, and this is what we're going to try to predict. And now, so there are a bunch of different labels, and now we're going to restrict the analysis to cats and faces. We're going to see if we can discriminate cats and faces. And for this, we're going to build a selecting vector that restricts, that is true only if the condition is either face or cat. Okay, and then we can apply it to the masked fMRI. And so if we apply it to the masked fMRI, now we have less time points because we've taken only the time points that were either faces or cats. And we're going to apply this also to the conditions, right? So, problem with partial execution of notebooks is that then you get an inconsistent state. This is why you should always execute a notebook in its order. Okay? So now I've selected 216 conditions out of my 1400 time points. And so now I have 2 things. I have a data matrix of 216 by 464 voxels, so 216 time points by 464 voxels, and I have the corresponding conditions. And now I can apply machine learning to this, and I can use an SVM. And so I'll use scikit-learn, and I'll use a linear SVM, so SVC with kernel linear, and I can just, so I can run this, and I can fit it on the data. So I just, scikit-learn, you just do fit the data and the labels to predict, and then I can predict. Okay, and I can predict, and I get a prediction. It looks fine. I'm predicting faces and places, and I can measure the error rate. So I can measure how many times the prediction is equal to the actual conditions. What fraction? And I get an error rate, well, a prediction performance of 1. So no error. Why is this meaningless? Because I have not separated out a test set. So I'm not validating my model on a test set. And as you've probably seen, you cannot trust a model prediction if it's not done on new data. You've not learned to generalize in any way. The reason being, I could just basically store this in an internal database, and if you show me a brain image that I've already seen, bang, I'm looking at my internal database, I've already seen it. I'm showing you this. This doesn't tell me I've learned any meaningful association between the brain image and the stimuli. So to measure prediction, what we need to do to measure prediction accuracy, what we need to do is we need to separate out some data, some test data. So for instance, we can separate out the last 30 data points. We can fit on all the data, but the last 30 data points, and then we can predict on the last 30 data points. And now if I do this, I have only 60% correct answer. I can do this using a for loop, using a k-fold object, which will successfully split the data in what I call train and test and do it again and again. When I test, I'm going to get different answers for each fold. And this can be done using scikit-learn with a specific function of scikit-learn that will basically do everything for you. It will do the cross-validation. It needs to take the learner, the data, the labels. Okay? And if I do this, I get the answers on each fold. So here I get 5 answers. So I have 5 folds. I can specify it using an extra argument. So I get the same answers here, but I can increase the number of folds. I can do 6 folds, for instance. If I do 6 folds, then I have different answers. And as many things in Nilearn or scikit-learn, I can do parallel computing. And if I say n job equals -1, I will use all the cores of my computer. And it goes faster. Okay? Now, ideally, to get good generalization, I should show that I'm generalizing to samples, to trials that are not my, nearest neighbor trial. I can generalize across to a new session. And to do this, I will use is this going to work? Where did I define the CV object? Oh, here. K-fold is the CV. So I will use, instead of k-fold, so this object is the k-fold object. And so now, instead of k-folding, I want to do leave one session out. And to do leave one session out, I will import a leave one group out. And I will give my cross-val score object a group index. So it's a label of each group. And for this, I will use the session label. And so if I do this, I now have generalization to a new session. And so you can count, I should have 12 numbers here because I have 12 sessions. Okay? If I want to do things better, I could do a leave P group out. Leave P group out. And I say I want to leave P equals 2. Now this is going to take longer because the combinatorics is bigger. And I'm going to use all the cores for that. And I got it wrong. It's not called leave P group out. I don't remember what it's called. Leave P groups out. Ooh, there's a mess. Oh, it's probably N groups. N groups, yep. There, it's working. Okay, and now I have much more. And this is a better estimate of prediction accuracy. Now I have -1 minute left, so I'm going to wrap up. Before I wrap up, I'm going to tell you how you can look at model weights, even though I've given you caveats on this. To look at model weights, we will need to retrieve the coefficients of the model, and these are vector, and we're going to turn them in a 3D image by using the inverse transform of the masker. And once we have this 3D image, we can look at it. It's now a nifty image, and we can either save it to file or look at it using a standard Nilearn object. And now further reading, well, you can redo this using, for instance, the SpaceNet object to use TVL1, and it's in the documentation, and then you can compare the maps that you get. And my time is over, thank you.
Okay, let's see if there are any other questions. Okay, Ben asks, when decoding, is there a straightforward way to unpack the black box so we can see what voxels are most responsible for driving effects? And I think that's what you're showing here.
I've showed this. I also, made a bunch of disclaimers in my lecture that this is an ill condition problem, and I can come up with all kinds of different maps that will predict as well.
But I think more broadly, maybe that. So how, given these kinds of things and all the caveats, what do we do to move forward on opening the black box of these models?
We get more data.
Get more data.
I mean, or we're bloody careful about what we say. I mean, I would say, SpaceNet and FREM are reasonably robust, but not completely. And one way of doing this is you can bootstrap your data, and you can look at how much your model weights vary. So you have no statistical control on them. You have statistical control on prediction. You don't have statistical control on the model weights. So sure, you can tell stories on things for which you have no statistical control, but.
Well, what do you think of sort of model interpretability methods like
Lime?
Blanking out on the name. This is Swinley here at UW. Maybe we can take that on Slack later.
No, I love model interpretability. It's super useful in everything. But model interpretability is two things. First, it's conditional on the model. Your model needs to be good. Second, if you have linear model, you don't need it. I mean, it's fine. I mean,
absolutely, yeah.
There's no issue.
I agree with both of those. Yeah, absolutely.
There's no issue. If you have linear models, your model interpretability will just find the model coefficients. But if your model is bad, it won't interpret them well.
Yeah, no, absolutely. I agree completely. Yeah, I think with complex nonlinear models, now you have to fall back maybe to locally linear approximations.
Which is Lime.
Yeah, exactly. Lime. That's what I was thinking about. Lime.
Yeah, I love Lime, by the way. But it's always the same thing. This is conditional on the quality of the model. So if you got a poor model, you'll get a poor interpretability. The question is, where can you find the code? Well, the code that I've used is the tutorial that you find in the examples at the top of the examples of Nilearn. So you can read it, run it, modify it.
Great. Thank you so much, Gael. And since there are no more questions, we can log off here and continue the discussion here on Slack and Neurostars and so on.
Okay, cool.
Take care. Bye.
Thank you.